Hi guys, so as we talked about on Thursday, today I'm just doing a short video just to explain position vectors for you. After this video, you should be able to do exercise 11D in the textbook. Okay, so let's say for example that we have a point here, 3, 2, and it's a coordinate point, and we want to translate it by the vector 4, 0. So you might think to yourself, well, I'm going to start off at 3, 2, and I'm going to apply the vector 4, 0, so I'll do 3, 2 plus 4, 0, and I'll end up at 7, 2. So vectors can only be added to another vector if this point here, so the coordinate point 3, 2, is treated as a vector. So at the moment, when it's written as a coordinate, it's not treated as a vector. If you do matrices in further maths, then you'll learn a little bit more about why these two could not be added. Basically, they both need to be in the same form. Okay, so they're not in the same form at the moment. This is a 1 by 2, and this is a 2 by 1. Okay. So what we could do, though, is to treat this as a vector, which will just be 3, 2, and then I add the vector 4, 0, and then I'll end up with 7, 2 there. So that would be absolutely fine, but we need to write the coordinate point as a vector. So if we're trying to show the position of a point from using a vector, then we're just going to call this a position vector. So basically, if you imagine, if I start off at the origin and I want to get to the coordinate point, then the vector to get to that point is just going to be, well, we know that it's 3 across on the x-axis and 2 up on the y-axis. So that's the point 3, 2. So we're describing how we go from the origin to that point. So 3 right, and then 2 up. So that's just how we can describe a coordinate as a position vector instead. So it will enable us a little bit later on to do all sorts of coordinate positions in all sorts of calculations, okay, so including matrix calculations, which we'll do in further maths, okay. So if we have the position vector of a point A, it's just a vector from the origin to get to A, so we'll write that as O to A, where O is the origin. Okay, so we sometimes write that as A as well in bold, just as it is written there. Okay, so if we have a look at this example here then, so we've got the point A has the coordinates 3, 4, and the point B has the coordinates 11, 2. So we want to know, in terms of A and J, the position vector of A and the position vector of B. So in other words, O to A and O to B. So the origin to A and the origin to B. So if we draw a little sketch here, everything's positive, so I just need the first quadrant there. So there's the origin. So maybe 3, 4 is here, so A could be there, and 11, 2 will maybe be somewhere over here, so that would be B there. So if I want the position vector for 3, 4, well, I've got to go 3 to the right and 4 up. So I could write it like that. And the position vector for B is just going to be 11 to the right and 2 up, so 11, 2. However, it did say in terms of I and J, so I'll write O to A as 3I plus 4J. Remember, if I'm handwriting it, I should just underline them to show that it's a vector. And then for B, it's just going to be 11I plus 2J. So on the last part, it wants the vector from A to B. So it says over here on the right-hand side, we could just have a look at that and think, well, if A is the point 3, 4, and B is the coordinate point 11, 2, what's happened from 3 to get to 11? So it's gone up, or it's gone to the right by 8. And then what's happened from 4 to get to 2? Well, it's gone down 2, so that's just going to be minus 2. So I could just write it like that by inspection, but if we want to do it slightly more formally, we could think of it in terms of the vectors there. So we want to find A to B, so we're looking for that vector there. So I know that O to A, I could call that A here, which is 3I plus 4J, and O to B is just here, and that is 11, 2, so 11I plus 2J. So if I want to go from A to B, I could follow this vector here, but let's pretend that I don't know what this is for a moment. We can see that another way to do that would be to go back to the origin and then to B. So that's what's happened here. So what I could write down is, in fact, there's a few more steps I need to take. So if I wanted A to B, I've got to go from A to O first, and then from O to B. Now, the problem is that I've already got O to A, but I haven't got A to O, but I know that that's just the negative of that. So it's just going to be minus O to A plus O to B. Or in other words, I could write that as O to B minus O to A. And that's where this has come from here. Okay, so I could write that with column vectors. I could say that O to B was 11, 2, and then O to A was 3, 4. So if I subtract those, I'll just end up with 8 minus 2 in the same way. So this here is just a formal way of doing that. So if you want the vector from A to B, then it's the same as the vector from O to B, so the position vector of B, minus O to A, the position vector of A. So A to B will be the position vector of B minus the position vector of A. This is just another example that shows exactly the same thing. So it just says, again, a position vector is fixed to the origin. Okay, so it's fixed relative to the origin. So if I have the point P, which is here at 4, 6, and the point Q, which is here at 3, minus 2, and we want the position vector, let's say, for example, of PQ. So we could just do what we said before. We could go from P to O and then O to Q. So O to Q is positive, but P to O, so positive Q, I mean there. And then P to O, well, I'm going in the opposite direction, so that would be minus P. And then add Q, or Q minus P, in other words. So Q minus P will just be 3 minus 4, which is minus 1. And then minus 2 minus 6, which is minus 8. And you can see on the diagram that that will work as well. So if I go 1 to the left, and 1, 2, 3, 4, 5, 6, 7, 8 down, and that will give me my vector there as well. Okay, so you can remember the formula if you like that we had a couple of slides ago, or you can just draw a little sketch for yourself like we've done there. Okay, so, and as we said, this is just a formal way of writing it there. So if O to A, or the position vector of A is x1, y1, so that's just a general point there. So we've got a general coordinate point, which is x1, y1. Our general vector therefore, or position vector, would be x1, y1. And then for B, it's a different point, so that's why we've got x2, y2, so it will be a different position vector, which is x2, y2. So in general, if I want the vector between the 2 points, so A to B, it's just going to be O to B minus O to A. So, and remember, you can always think to yourself that wherever A is, if you want to go from A to B, then, and you know what the position vector is, so you know how to get back to the origin, you can always go, the O to A would be going in, going up from the origin to A, so O to A would be going in that direction, so you have to go back to the origin, so that's why O to A will be negative, and then you go up to point B. So that's where this comes from there, okay? And you can write that generally there, or you can write it in terms of I and J as well, okay? Okay, so for this question here, it says we've got points P is 4, 6, and Q is 3, minus 2. It says, let M be the midpoint of the line PQ. What is the position vector of the point M? So if we're to do this, then there's actually a few different ways that we could do this. So it says O to M, so here to here. We just need to find a way to get there. So we could go from O to P, and then halfway down P to Q. So that's why it's half P to Q there. So we know that O to P is P. And we can also figure out that if I want to go from P to Q, well, I don't know this way, but this way I could write as minus P plus Q, or Q minus P. But I only want to go halfway down there, so that's why it's a half there. Then all we have to do is just collect our like terms. So I've got P minus a half P, which just gives me half P. So remember, 2 halves of P minus 1 half of P gives me half P there. And then I've just got half Q there. So I could write it as half P plus half Q, or just half P. So this is another way that we could have done that as well. So if I've got 4, 6, and q is 3 minus 2, so we could think of it in the way that we've just done. So that would be, if we went back a side, so we've got half of a plus b. So in this situation, it would be half of p plus q. Or what you could also think is if I were to put these two together, so this isn't going to work out completely well because we haven't got all of the squares needed here. So if I added together p plus q, so at the end of p, I'm just going to go 3 right and 2 down. So I'll end up, say, about here. And what you might notice, so if that is q there, then this is just going to be, or m is halfway along that. So if you wanted to find that, then all we can say is that we could add the 2 points together, or the 2 position vectors there, and we could halve it. So if you want halfway along those, that's all that you need to do there. Okay, so this is an example from the book. So we've got O to A is 5 minus 2j, and A to B is 3i plus 4j. Find the position vector of B. So there's a few different ways that you could do this. You could draw a sketch if you wanted to. So let's just draw it out like this. So O to A, so obviously here's the origin. So A would be around about here. And then to go from A to B, I've got to go 3 to the right and 4 up. So B is somewhere around about here. So I need to figure out the position vector of B. So we could use our diagram to help us if we wanted to, and we could just write it as a diagram. So we've got, that would be to go from O to A, I've got to go 5 right and 2 down, and to go from A to B, I've then got to go 3 right and 4 up. So if I want O to B, I could just add those 2 vectors together, and I'll have 5 minus 2 plus 3, 4, which is just going to give me 8, 2. So O to B is equal to 8, 2. However, I'll just write it in ij notation, so it's going to be 8i plus 2j. Another way you could have done this is you could have used that general formula that we were talking about earlier. So if you want the vector from A to B, we said that that would be equal to the vector of O to B minus the position vector of A, O to A. So if you rearrange that and you want the position vector of B, you can add the position vector of A to both sides, and you'll get that the position vector of B, O to B, is equal to A to B plus O to A, which is essentially exactly what we were doing there, that we've just gone from O to A plus A to B. And it doesn't really matter, we could, vector addition is commutative, it means we can do it in any order, so O to A plus A to B is the same as A to B plus O to A, so that will be exactly the same thing there. The next part is find the exact value of O to B, the magnitude of O to B in simplified surd form. So once we've got that, let's just do part B just here. O to B is equal to, let's write it as a column vector this time, so 8, 2. So if I want the magnitude of that, then it's just going to be, using Pythagoras' theorem, the square root of 8 squared plus 2 squared. So that's going to be the square root of 64 plus 4, which is just going to be the square root of 68. Because it asks for it in simplified surd form, I'll need to try and simplify my surd. Obviously, you can write it in your calculator, or you could say that it's going to be 4 goes into 68, so that's going to be root 4 times root 17, so that will be 2 root 17. Okay, so hopefully you should have enough knowledge now to have a go at exercise 11D. So don't do all of the questions, just the ones that I've put on show my homework. So obviously you can do more than that if you want to, and make sure you're checking your answers in the back of the book as well. Just be careful, because if the answer is a surd and you've not simplified it fully, your answer might be different to the one in the book. Okay, have a good week. Bye-bye. So here's exercise 11D.